Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Anil Sir, and in this session, we are going to discuss about pipelining and vector processing. What exactly is this session all about? In fact, we people are in the crash course. For the past 3 days, we covered a whole lot of topics. The first one that we covered is the instruction set and the addressing modes. Next one is the memory. In this session, we are going to cover the most important topic, that is pipelining. It is one of the most important topics because you will be able to get full out of full if the questions are from pipelining, because the pipelining is a topic where you can score the maximum marks, because the questions will be straight, the formulas will be simple, and if you actually can get the formulas, we'll be able to crack all the questions within pipelining very easily indeed. Hi Arshita, very good evening. So without wasting any more time, let me take you people into the session. This is all about myself. This is Anil Sir. I do have a 13 plus years of experience, and for the past 13 plus years, I've been training in the GATE, and I've been teaching everywhere in India, including Andaman and Nicobar and Srinagar. I'm a triple PG holder. I did my MS in Information Technology, MSc in Mathematics. I also did my MBA. Now, one important session coming live in your way, and 22nd November 8 p.m. And this is one of the important sessions because GATE 2024 is ahead. 2023 is almost over. For those aspirants for those who aspire GATE 2024, this is the right session to attend, because you will get to know many details about the GATE 2024, and you are going to get an idea. You are going to get a view on your career. You are going to get a comprehensive view at your career. What is the importance of the GATE? What is the importance of so many factors that are going to make you people appearing for the GATE? The session coming live on your way from the 22nd November 8 p.m. which is going to taken by Mr. Anil Sir, and who is an alumni of MTech NIT Trichy, and he has 11 plus years of experience. Now, once again, for one more time, let me admit that this is the right time for preparing for the mock test. Hi Chitra, hi Anu, hi Krishna, hi Arshita, very good evening. This is the right time for the mock test. Please do give the mock test, please do attend the mock test. And the mock test will be live for one more day, because today is 21st, 22nd also mock test will be available. Do get registered if you haven't already yet, but give the mock test which is precise and more important for the GATE 2023's aspect, because this is the right time for the mock test and the preparation. Alright, so do not miss this chance. Do get registered to the mock test and give and wait for the result at 23rd of this November. Now, this session is all about, we are going to talk about a parallel processing. Let me tell you, stay with me. We are going to completely discuss about the pipelining. Pipelining is a very simple concept. The pipelining, the total concept can be explained in completely 10 to 15 minutes if you stay focused. There is nothing much. But if you actually can understand the glance of the pipelining, you will be able to solve any question on the pipelining, because the pipelining is, hi Sri Lakshmi, very good evening. Pipelining is such a wonderful topic which is very easy, at is going to give you, it is going to fetch you full out of full if the questions are given from the pipeline. I'm expecting one question from the pipelining. Let us see in 2023. So in this session, we're going to discuss about what is parallel processing and what is throughput and what exactly is the data pipeline. Next to the data pipeline, we also will discuss about something called an instruction pipeline. This is the session's agenda. Let me take you people directly into the session. The first of all, why do we require pipelining? Let us stay focused and understand. The thing is very simple. See, if you are a designer, belongs to the computer system, no matter what kind of a designer you are, you can be CPU designer, you can be ALU designer, control unit designer, or you're a main memory RAM designer, or you're a software designer. But understand carefully, no matter what kind of a designer you are, if you are a designer related to the computer system, your fundamental objective is only one thing, that is increasing the throughput, improving the throughput. Okay, This throughput must be improved all the time. Today my throughput may be something. Tomorrow I need to work on how can I improve my throughput further. Day after tomorrow I can improve my throughput even more further. This is always the fundamental objective of any designer. But for that, we just need to understand what is a throughput. Throughput at the core level of the computer system, forget about everything. When you talk about the throughput sitting at the core level of the computer system, there may be a number of definitions at the high end. But if you understand the throughput as a designer, there is only one definition for the throughput. The throughput is simple. Number of instructions per second. Let me put it this way. Number of instructions per second. This is what the throughput. As a CPU designer, you should be always striving very hard to increase the number of instructions that can be executed in 1 second. But understand carefully how we will be able to increase the number of instructions per second. A simple calculation. Let me tell you. Let us say I do have a 1 gigahertz CPU. A 1 gigahertz CPU, this is the capacity of my CPU. Let us understand and stay focused. See, if the capacity of 1 gigahertz CPU is 10 power 9, chunks a second. The capacity of 1 gigahertz CPU is 10 power 9 chunks a second. Sir, what exactly is this? Let me tell you. In 1 gigahertz CPU, 1 second is divided into 10 power 9 time units. And each time unit is a nanosecond. Understand carefully. If you are capable to execute one instruction at 1 nanosecond, that means that you will be able to execute 10 power 9 instructions a second in a 1 gigahertz CPU. Correct? But the thing is, it is not practical. Practically, we won't be able to tap the potentiality of the CPU. Practically, we won't be able to meet this rate of 10 power 9 instructions per second. CPU is capable of executing 10 power 9 instructions per second, but there are several practical hazards. There are several practical limitations. Because of those limitations, initially maybe let us say I am able to execute only 10 power 4 instructions per second. Then tomorrow I just need to increase because the total productivity that I can reach is 10 power 9. But as this is not practical, we may initially stick to 10 power 4. But the maximum potentiality is 10 power 9. So I need to bring this to 10 power 5 tomorrow. I need to bring this to 10 power 6 tomorrow. So this is always a striving for a designer. We should always keep on focusing how we will be able to increase the throughput. Okay. But understand carefully. Understand carefully. What is the possibility of increasing the throughput? What is the best way of increasing the throughput? Let us forget everything. If I ask you a question, give me an idea how I can improve the throughput. Rather, in the simplest question, in the simplest way, if I can put it at the core, how we will be able to execute more number of instructions per second. This is what I defined as CPU. Defined a throughput, right? How we will be able to execute more number of instructions per second. If the question is asked, what will be your answer? Simple. Most of the people will give me only one answer. Sir, please improve. Rather than executing only one instruction at a time, execute more instructions in parallel. This might be the idea you may be giving to me when I ask you how we will be able to increase the throughput. Alright? But understand one more thing. We won't be able to execute instructions parallelly in a single CPU. If I have a single CPU, my single CPU, if I have a single CPU, my single CPU is capable of executing only one instruction at a time. One instructions at a time. What exactly is happening? One instructions at a time. Just a minute. Yeah. Why? Because simple. A single CPU will not be able to execute more number of instructions. A single CPU will be able to execute one and only one instruction. If you want to execute instructions parallelly, you need to have several CPUs with you. but it is not practical. I can't have a multi-process system as my desktop. Simple. A multi-process system will be very costly here. So in a single process system, how will I be able to execute more number of instructions per second? Let me put it this way. Simple. The term parallel processing, the term parallel processing actually has been a brainchild of some guy who's called Mr. Am I audible? Yeah. Yeah. The term parallel processing actually defines something. See, if you want to understand parallel processing, you need to understand your main memory. In the main memory, there are two chunks. One is instruction chunk, one more is data chunk. Stay focused. And when an instruction has to be executed, first of all, we should be able to fetch the instruction from the memory. And for executing every instruction, I require to collect a few data operands from the data memory. Alright. Now, keeping this one in his mind, some guy called Mr. J.J. Flynn. This J.J. Flynn actually defined the term parallel processing. Okay. This parallel processing actually has been defined in 4 ways. The first one is single instruction stream, single data stream. That is, all the instructions that are going to be fetched by the CPU is going to constitute something called an instruction stream. All the instructions that are going to be fetched from the data memory is going to constitute something called a data stream. Got me? So, if a system has only one instruction stream and one data stream, that will come under single instruction stream, single data stream computer system. And the next thing is, some computer systems will have multiple instruction streams, single instruction stream but multiple data streams. Those computer systems are slightly faster than SISD systems. Some computer systems are of MISD, multiple instruction stream and a single data stream. But let me tell you, multiple instruction stream and a single data stream is not possible because this is not practical at all. Why it is not possible, we'll discuss in some other session, because we only will focus on SISD systems where pipelining will get implemented. Final one is MIMD systems. So what is MIMD systems? In the MIMD systems, we have multiple instruction streams and multiple data streams. But you can clearly understand there are several things here. SISD, single instruction stream, single data stream. There is only one instruction stream, there is only one data stream. Single instruction stream, multiple data stream. There is one single instruction stream. To support that, we have multiple data streams. It is slightly faster. MISD, there is no application. MIMD, it is purely for multiprocessor system. It is purely for multiprocessor system. But understand carefully something. Understand carefully. This is single instruction stream, single data stream. What exactly is this system? This system is your CPU. This system is my desktop. This system is the computer system that what we are working on. These are the systems where we are going to do our daily tasks. It could be either your laptop or our desktop. That means that our computer systems has only one single instruction stream, has only one single data stream to support. This SISD system doesn't have any parallel processing capabilities. It doesn't have. So then what is the case? How would we be able to improve the throughput in SISD systems? Simple thing is, if you want to improve the throughput in SISD systems, you need to adopt a technique which is called pipelining. You got me? So anyhow, all the other systems are faster than SISD systems. But if you want to make SISD systems faster, you need to adopt a technique called pipelining. Got me? So what we will do is, we will involve the concept of the pipelining, implement the concept of pipelining in SISD systems to increase the throughput of the system. Now, let me tell you what exactly is pipelining. The pipelining definition is as on your screen, first of all. But anyhow, the definition is the definition, but we have to go to the core of it, right? But what exactly is this pipelining will tell you. Let us not look at the definition initially. Let us understand the pipelining concept straight away with the simplest words as possible. For an example, I have one instruction. The instruction is, let us say, x plus y plus z divided by 2 into a mod s. There is an instruction. This is a complex arithmetic instruction, right? But understand carefully, where this instruction has to get executed, that instruction has to get executed in our ALU, right? In the ALU, this total instruction will get executed. Define ALU. What is ALU? Of course, my ALU is capable of performing every operation in it. My ALU is capable of performing addition, subtraction, division, multiplication, ALU, where we're going to perform the operation. But understand carefully, my ALU, although it is capable of performing any operation, but it will be able to execute one and only one operation at a time. It can perform wide variety of operations, but only one at a time. Got me? So the thing is, understand. What we will do is, this ALU, I'm going to divide it as multiple segments. This is segment 1, this is segment 2, this is segment 3, this is segment. I will divide my ALU as many segments as possible. My ALU is able to perform arithmetic operations, logic operations, and shift operations. Several arithmetic operations, several logic operations, several shift operations. So what I will do is, for each arithmetic operation, I will use a segment. Let us say this is for addition. Any operation which is addition will directly get into this addition segment. Let us say subtraction. Any operation which is subtraction, that will get into that segment. Got me? So what I will do is, rather than making ALU performing only one operation at a time, I will divide the capabilities of the ALU into several segments, where each segment is capable of performing one certain operation of the ALU in parallel to the other segments. It can operate parallelly to the other segments. So let us have a look at the definition of the pipeline. It is a technique of decomposing a sequential task into several subtasks, where each subtask will get executed in its own and dedicated segment, which is what the definition of the pipeline. Now, let me give you a complete idea about the data segment straight away. Okay, so this is already I told you, single instruction, single data stream. Now, see, have a look at this. Here the thing is, this is my ALU, right? This is the ALU. This is a pipeline ALU. Have a look at this. Generally, let us have a look at on your left side on the screen. Here, this one is the ALU, which is not segmentized. This is a single unit of the ALU, which every operation is going to get performed only in this unit. Only in this unit. But here, the same ALU has been segmentized. Both are the same. These both ALUs can perform any operation. But when you look at this ALU, all the capabilities of the ALU have been divided into several segments. Now, there is an adder subtractor. In this adder subtractor units, addition and subtraction is going to get performed. Integer multiply. Here, multiplication will get performed. It is the logic unit, where logical operations will get performed. Shift unit, shift operations will get performed. Incremental, increment operation will get performed. Again, we have one more floating point adder subtractor. Now you can clearly see the capabilities of the ALU have been divided into several segments. Got me? Now, pipelining, now if you actually can focus on, it is just all about segmentizing, right? Now, what we will do is, straight away we will understand the concept of the pipeline by designing one data pipeline system. For that, let us take an example. The example that what I am going to take is, I just want to execute this instruction, A into B plus C, rather AI into BI plus CI. Now understand carefully. See, in order to perform, what are the operations? Initially multiplication to be performed, followed by addition to be performed, right? So if you take a ALU which is non-pipeline, how many clock cycles are actually required to perform this operation? Stay focused. I have taken an ALU which is completely non-pipeline at all. At that time, in order to perform these operations, let us say for multiplication, let us say there is one clock cycle. I require to take one clock cycle. For addition, I require to take one more clock cycle. But there is something called operand fetch also. Operand fetch will require one clock cycle. So if you want to perform A into B plus C, initially operands must be fetched. It will take one clock cycle. A, B, C must be fetched into the ALU. That will take one clock cycle, right after which multiplication will get performed. That will take one more clock cycle, and addition will have to perform. That will take one more clock cycle. But understand, this instruction will execute in a loop. For how many times loop gets repeated? Loop gets repeated, as you can see, for the 7 times, because AI into BI plus CI, where I is equal to 1, 2, 3 till 7. So as long as the I value is supplied, the instruction will get executed. That means that I do have a total of 7 instructions. I do have a total of 7 instructions. Each instruction is taking 3 clock cycles. Right? Now, the total number of clock cycles in order to execute these 7 instructions is 7 into 3, 21 clock cycles. I have 7 instructions which are to be executed in a non-pipeline system, which takes altogether a total of 21 clock cycles. But understand, the same can be executed in a corresponding pipeline system. In the pipeline system, what I will do is, I will divide all these activities into 3 different segments. Right, Krishna? We need to divide the total activities into 3 segments, because actually we have 3 activities. The first activity is fetching the operands. Second activity is multiplication, and the third activity is, the addition. So what we will do is, what you are watching in this screen is, there is a data pipeline in which we can find 3 segments. In the segment 1, which will perform. In the segment 2, multiplication will get performed. In the segment 3, addition will get performed. Got me? So stay focused and understand how many clock cycles actually are required in order to perform same operation A into B plus C. Initially, understand carefully, one thing is the biggest rule of the pipeline. In between every stage, I require an intermediate register. These intermediate registers are actually required in a pipeline system in order to get the operand from the previous segment, give that as an input to the next segment. Let us say from the multiplication segment to the addition segment, there has to be the data supplied. For that, I will use an intermediate register. So in between the segments, I just need to use intermediate registers. Now you can clearly see. Now A and B must be sent to the multiplication segment. This multiplication segment has 2 registers. Now initially A value will be sent to R1, B value will be sent to R2. R1 and R2 will be sent to multiplication. Then the multiplication segment output will be sent to R3. From the R3 to addition. But now addition also need to collect the operand from C. But C to adder, we use one more intermediate register. From that register will collect the operand from C, will feed it to the addition segment. Finally, this addition is going to perform the addition in between R3, which has the product of A and B, and R4, which is simply C. Finally, it will send to R5. Let us understand the things that are going to happen in a respective clock cycles. In the first clock cycle, what will happen? A1 and B1 will get sent to R1 and R2, right? In the second clock pulse, what will happen? In the second clock pulse, this multiplication segment is going to perform the operation and send it to R3. That means that in the second clock pulse, A1 into B1 is available. The product of A1 and B1 is available in R3. But same time, at the second clock pulse, as the R1 and R2 are free, R1 and R2 will get the values from A2 and B2. At the same time, in the second clock pulse, R4 will get the value from C1, right? Okay, so what will happen? In the third clock pulse, R5 is going to perform the addition in between R3. What is R3? R3 is A1 into B1 plus C1. What is R4? C1. So, in the third clock pulse, we will get the first output. Already in the third clock pulse, what happened? R3 is free. R3 will get its second values, that is from A2 into B2. Okay, in the third clock pulse, R4 will have C2. In the third clock pulse, R1 and R2 will have A3 and B3, right? So you can clearly see in the pipelining systems, in the first two clock pulses, there won't be any output at all. But right from the third clock pulse onwards, there will be continuous output. Because after the third clock pulse, in third clock pulse, we got the first product, A1 into B1 plus C1. In the fourth clock pulse, what you will get? A2 into B2 plus C2, right? So this is how the pipeline system is going to completely change the scenario of the system. Earlier, how many clock cycles are actually required? The total number of clock cycles that are required by the system is equal to 21. Right now, the total number of clock cycles required in this pipeline system, if you think carefully, I will show you table. Simple. In the first two clock pulse, there won't be any output. Right from the third clock cycle onwards, there will be continuous output. Got me? So what will happen? Total number of clock pulses is equal to the wasted clock pulses in the pipeline system plus the total number of instructions, since each and every instruction is executing one clock cycle right from the third clock cycle onwards. So pipeline system time is equal to, I would say, pipeline time for executing 7 instructions is just equal to 2 clock cycles, which are wasted clock cycles, plus 7 clock cycles in which we do have the total output, which is equal to 9. You can see in the non-pipeline system it was equal to 21. In the pipeline system it is equal to 9. Now you can see the speed up is equal to, I will write here, the speed up is equal to 21 divided by 9 is equal to 2.33. Now in this pipeline system, we got a throughput which is more than double. The pipeline system completely improved from a non-pipeline system. More than 100% throughput we got from the pipeline system. So what exactly is this? Let us understand. What is the pipeline time? What is the non-pipeline time? Stay focused and understand carefully. Okay. See, non-pipeline system time given by something called, I will write it here, non-pipeline system time is equal to n into Tn. What is n? N is the number of tasks. Tn is time per task, time per task. Okay, here if you take the same example, n was equal to 7. N was equal to 7 in the previous case. Time required for one task is equal to 3 clock cycles. 7 into 3 was equal to 21. Now in a pipeline system, I will write it here. Pipeline system time is equal to, let me tell you, there are a total wasted clock cycles, right? Initially, for the first 2 clock pulses, there is no output at all. I can tell you, the wasted clock pulses are equal to k minus 1. For these k minus 1 clock pulses, there won't be any output, where k is the number of segments. Okay, if you stay focused, the total number of segments in the earlier case is equal to 3. So for how many clock cycles there was no output? For k minus 1, 2 clock cycles there was no output at all. Right after which, for every next clock pulse, there is an output. So pipeline time can be given by k minus 1 plus n into Tp. Sir, what is Tp? Tp is, understand carefully, let us say there are 3 segments in the pipeline. Okay. Now we understood that, we assume that Each and every segment is taking only one clock pulse. First segment is fetch the operand, second segment is multiplication, and the third segment is addition segment. We assume that each and every segment is taking only one clock cycle. But understand carefully, in general, in practical, it won't be true. Different segment takes different clock cycles. Fetch, let us say it may be one clock cycle, multiplication may be 3 clock cycles, addition may be 2 clock cycles. At that time, what will happen is TP will become max segment delay. So, pipeline time is equal to K minus 1 plus N into TP. TP is max segment delay. Let me write down the TP also. TP is equal to max segment delay. There will be one more component added to this, that is max register delay. What Krishna told is perfectly right. Max register delay. This is what TP all about. Simple. This is the only rule that you need to learn in pipelining. So let me list out all the possible rules of the pipeline. Stay focused, which is more important for the next 5 minutes. What the formulas that I am going to put it before you are very important to crack the GATE exam, especially when you get a question from pipelining. Let me erase everything. Initially, I would say speed up is equal to non-pipeline system n into Tn divided by K plus n minus 1 into Tp. Speed up is equal to NTN divided by K plus n minus 1 into Tp. Stay focused. Here, if we are provided with the number of tasks, this is the rule to follow. If we are not provided with the number of tasks, speed up will be equal to, in case no task, Tn divided by Tp only. In the question, if you are provided with the number of tasks, then you can apply the rule NTN divided by K plus n minus 1 into Tp. But if you are not provided with the number of tasks, Tn will just be limited to Tn divided by Tp. Why? Because I will tell you, n and K plus n minus 1 we actually can cancel. See, between n and K plus n minus 1, the difference of the factor is just K minus 1, right? This K minus 1 factor will be very limited so that we can ignore that. Initially, only for the first 2 clock cycles, there will not be any output, right? But how many clock cycles are there when the system is running? When the system is running, there will be so many clock cycles, lakhs and crores of the clock cycles. So, K minus 1 will be negligible actually. Okay. So, if I can cancel nn K plus n minus 1, we got just Tn divided by Tp, right? So, if the number of tasks are not provided, you can use this rule to get the speed up. This is what the speed up of a pipeline system. Sometimes what will happen is we need to calculate pipeline time with stalls. When you are asked to calculate average pipeline time with the stalls, one more simple rule you can apply, that is 1 plus R into S, 1 plus R into S into Tp. What is R? R is rate of instructions causes stalls. Okay. S is the stall cycles. And 2 more additional you require. What is a stall cycle? The stall cycle calculation is, write it down, stall cycles is equal to K minus 1, and one more rule is TP is equal to max segment delay plus max register delay. Okay, this is an important thing to understand. These are the only formulas of the pipelining. Speed up n into Tn divided by k plus n minus 1 into Tp. Average pipeline time with the stall. Sometimes things can go really awry. Things can go really catastrophic because of the stall cycles. Stall cycles will seriously impact the performance of the pipeline systems. I've taken one class, separate class in YouTube for stall cycles. But anyhow, when we are provided with stall cycle, the pipeline time with the stall cycle can be calculated with 1 plus R into S into Tp, where R is the rate of instruction that incurs the stalls and S is the total stall cycles. Okay, and stall cycles can be easily calculated as k minus 1, the total number of segments minus 1, and the Tp is max segment delay plus max register delay. These are the formulas of the pipeline. But understand? Let me clear this. Write it down. See, this is how a generalized pipeline looks like. Let us say there is an instruction pipeline. Okay. The instruction pipeline, sir, what is there in the instruction pipeline? Understand carefully. What is an instruction pipeline? Instruction pipeline is going to segmentize the stages of the instruction cycle. What are the different stages of the instruction cycle? If you can have a look at the stages in the instruction cycle, there are predominantly 4 stages in any instruction cycle, starting with instruction fetch. Followed by instruction decode, followed by operand fetch, followed by execution. Okay, now let us say these are the 4 stages of the instruction pipeline. During every instruction execution, first of all, instruction must be fetched, followed by instruction to get decoded. Next one is operand to be fetched. Finally, execution will happen. Now the thing is, if it is a single CPU, let us say each and every instruction will take 1 clock cycle to perform this operation. For fetching, 1 clock cycle, decoding, 1 more clock cycle, operand fetch, 1 more clock cycle, and execution, 1 more clock cycle. So how many clock cycles are required for one instruction? One instruction requires 4 clock cycles. But understand, if you can divide into multiple segments, say this is instruction fetch, instruction decode, operand fetch, and execution, you can clearly see when the first instruction is here, second instruction will wait outside. When the first instruction comes in here, second instruction will come here. First instruction will come here, second instruction will come here, third instruction will come here. So when the first instruction is in the final segment, second instruction will be in the third segment, third instruction will be in the second segment, fourth instruction will be in the first segment. Right after, you can clearly see, have a look at this. Right after the 3 clock pulses, understand, in the first clock pulse, instruction fetch will happen, the data will be available here. In the second clock pulse, instruction decode will happen, the data will be available here. In the third clock pulse, operand fetch will happen, the data will available here. In the fourth clock pulse, completely instruction will get executed. In R4, we get a result. That means that in which clock pulse we got the output? At the fourth clock pulse, we got an output. That means that in a pipeline system, the total wasted clock cycles is equal to 3. What is 3? 3 is the factor of k minus 1. The k is the total number of segments minus 1. K is equal to 4 here, minus 1 is equal to 3. I hope I made my point very clear indeed. This is the instruction pipeline. Let us see. I am going to, this is the space-time diagram that I already explained. This is all explained. Speed up also explained. Let us start solving a few questions straight away without wasting any more time. Since we have discussed almost every in the pipeline within no time. So the first question is on your screen. The first question is, the stage delays in a 4-stage pipeline are 800, 500, 400 and 300 picoseconds. 4 stages in a pipeline are 800, 500, 400 and 300 picoseconds. That means that There are 4 stages in a pipeline. The first stage time is 800 picoseconds. Next stage time is 500 picoseconds. And the third segment time is 400 picoseconds. And the fourth segment time is 300 picoseconds. Now, what is pipeline time? The pipeline time is the TP. Okay. Pipeline time TP is the max segment delay, right? Yes or no? What is the max segment delay? Max segment delay, the pipeline time. Remember something. If somebody asks you what is the pipeline time, simply you just find it out which segment has the maximum delay. That is your pipeline time. That means that every instruction requires 800 picoseconds in this case. Every instruction will take 800 picoseconds. Now TP is equal to 800 picoseconds. Thank you, Krishna. Thank you so much. Thank you so much for, anyhow, let us go ahead with the session. The next thing is the first stage. According to the question, the first stage with delay 800 picoseconds is replaced with a functionally equivalent design involving 2 stages with respective delays 600 and 350 picoseconds. The throughput increase of the pipeline is -%. Now, according to the question, we have 2 different pipeline systems. This is the first pipeline and there is second pipeline. In the second pipeline, there is a small change. There is a slight change is implemented in the first pipeline system. In the second pipeline, what happened is this is divided into 2 segments. This 800 is divided into 2 segments. One is taking 600 picoseconds, one more is taking 350 picoseconds, and all remain the same. This is 500 and this is 400 and this is 300. Now, what is the throughput difference? There is a pipeline 2 and there is pipeline 1. What exactly is the throughput difference? If you can calculate, simple. The first one is 800 picoseconds. Second one TP is equal to 600 picoseconds, right? The maximum segment delay is 600 picoseconds. The maximum segment delay in the pipeline 1 is 800 picoseconds. Now, when you can have a focus, in the second pipeline, the throughput is increased by 200 picoseconds. Earlier, one instruction was taking 800 picoseconds. Now, it is just taking 600 picoseconds. Now, what is the throughput improvement? Throughput improvement is 200 picoseconds. Throughput is improved by 200 picoseconds. Simple. What is the percentage of 200 in 600? Obviously, it is equal to 33.33, right? The total throughput improvement is 33.33 is the correct option in this case. Let me take you people to the next question. Consider the following code sequence having 5 instructions, I1 to I5. Each of these instructions has the following format. Add R1, R2, R3. The first instruction is add R1, R2, R3. Second instruction is MUL R7, R1, R3. Third instruction is SUB R4, R1, R5. Fourth instruction is add R3, R2, R4. And the fifth instruction is MUL R7, R8 and R9. These are the 5 instructions and there are a few statements given. We need to find out which is the correct statement, which is the incorrect statement. But first of all, before I take you people into that, I need to discuss something about the pipeline hazards. There are something called data hazards. Okay. There are 3 kinds of data hazards. The first hazard is, I will tell you, is a raw hazard. This raw hazard can also be called as a true dependence. What is true dependence? What is the example for true dependence? True dependence. Understand carefully. For this, I need to clear. See, there are 2 instructions. X is equal to A plus B. y is equal to x plus z. Okay, when you look at these two instructions, the first instruction's destination operand is the second instruction's source operand. Okay, then that means that we are in a situation called that the second instruction is a true dependent instruction of the first instruction. You can clearly see, unless the first instruction is completely executed, you can't execute the second instruction at all. There is a dependency. Dependency is the difficulty in the pipeline. This is either called RAW dependency or a true dependence. Both are one and the same. So first instruction output is second instruction input. Then that means that we are in a situation called true dependence. Okay. Next thing is the anti-dependence. What is anti-dependence? Stay focused. Anti-dependence meaning this anti-dependence or WAR. Both are one and the same. But what exactly is this? Now, if the situation of earlier case is reversed, then we are in a situation called anti-dependence. For an example, y is equal to x plus z. Okay. X is equal to a plus b. You can clearly see this is the reverse case of the previous one. The first instruction's source operand is second instruction's output. Then this is something called an anti-dependence. What is an anti-dependence? Anti-dependence meaning the first instruction's source operand is the second instruction's destination operand, output operand. Then we are in a situation called anti-dependence. What is the third one? WAW or output dependence. Okay, simple. For both instructions, output operand is the very same. For an example, x is equal to a plus b and x is equal to y plus z. These are the two consecutive instructions. For those two continuous instructions, output is the very same. In such case, we are said to be in a situation called output dependence or WAW hazards, WAW hazard. Keeping these things in our mind, we should be able to solve these questions. The first question is, this data that is given for the question is I1 is equal to some, let us say some statements are given. Look at the statements straight away. There is an anti-dependence between instruction I2 and I5. What is anti-dependence? What is an anti-dependence? First instruction's destination operand, rather source operand is second instruction destination operand. Alright. Now look at I2. In I2 we have R7, R1, R3. Okay. R1, R3 are the source operands. If I5 has any of these two operands as the destination operand, then that means that we are in a situation called output dependence, anti-dependence, right? So where is I5? I5's output is R7. I5's destination is R7. It is neither R1 nor R3. So it is not correct. S1 is not correct. Okay. We will have a look at S2. Now, there is an anti-dependence between I2 and I4. Let us have a look at I2, the same instruction in which operands are R1 and R3. The source operands are R1 and R3. Again in I4, any of these R1 and R3 are the destination operands, are the output operands. Then we have the output dependence on cards. So I4 is, you can clearly see R3, which is the source operand in I2, now is the destination operand in I4. So that means that between I2 and I4, there is an anti-dependence. Between I2 and I4, there is an anti-dependence, right? So second statement is true and correct. We will see if the third statement is correct or not. With an instruction pipeline, an anti-dependence always creates one or more stalls. This is always true. See, no matter which dependence it is, if there is a dependence, there will be a stall. It could be anti-dependence, it could be an output dependence, it could be true dependence, anything what you say. These dependencies are called the difficulties in the pipeline. If there is a difficulty present, there will definitely be stalls. So S3 also is correct. S2 and S3 are only the correct options, but not S1 in this case. So S2 and S3 are the correct options. Option D is correct. Next question, excuse me, this is I'll explain. Yeah. Consider a non-pipeline processor with a clock rate of 2.5 GHz and average cycles per instruction of 4. The same processor is upgraded to a pipeline processor with 5 stages. But due to the internal pipeline delay, the clock speed is reduced to 2 GHz. Next question is, it is one of the PYQ. Stay focused and understand. Consider a non-pipeline processor with a clock rate of 2.5 GHz. There is processor 1, I would say. Processor 1, which is a non-pipeline processor. The clock speed of the non-pipeline processor is equal to 2.5 GHz. Okay. And it is also given that average cycles per instruction of 4. That means that within this processor, one instruction takes 4 clock cycles. In P1, non-pipeline processor, one instruction is taking 4 clock cycles. Of course, the same processor is upgraded to a pipelined processor with 4 stages. Now, this has been upgraded to a pipeline processor. There is processor P2. In P2, the total number of segments K is equal to 4. Okay. But due to the internal delay, the clock speed is reduced to 2 GHz. Here, clock speed is equal to only 2 GHz. Okay. Assume that there are no stalls in the pipeline. There are no stalls. The speed up achieved in this pipeline processor is what? Simple thing is, here there is a pipeline 1. For that, clock cycle is equal to 2.5 GHz. Okay. Here in a pipeline system, the clock cycle is equal to 2 GHz. What is the speed up? Simple. Okay. Now, with a simple explanation, I will make it very clear. I would say speed up is equal to non-pipeline system time, right? What is a non-pipeline system time? Non-pipeline system, one instruction is taking 4 clock cycles, right? 1 into 4 clock cycles. Divided by pipeline time. In the pipeline, as I don't need to explain, one instruction will take only 1 clock cycle. If there are no stalls, write it down somewhere. In the pipeline, one instruction will take only 1 clock cycle. 1 into 1 clock cycle only. Okay. That means that I can ignore this one. What is 4 clock cycles? 4 clock cycles is equal to 4 into what is 1 clock cycle time? 1 clock cycle time is equal to 4 into 1 by 2.5, because time is equal to 1 by frequency, right? 4 into 1 by 2.5 divided by 1 clock cycle here in the pipeline system is equal to 1 by 2. Got my point? So this will become 8 by 2.5 divided by 1 by 2, which is equal to 4 by 2.5 divided by 1 by 2, which becomes 8 by 2.5. 8 by 2.5 is equal to, if I am not wrong, just a minute. .2 clock cycles. So the speed up is equal to 3.2 clock cycles. Okay, I hope I made my point very clear here. Okay, next question is, the final question for the day is on your screen. The 4-stage pipeline has the stage delays 150, 120, 160 and 140 nanoseconds respectively. Registers that are used between the stages have a delay of 5 nanoseconds each. Assuming the constant clocking rate, the total time taken to process 1000 data items on this pipeline will be dash microseconds. Simple. Here, the total number of segments in this, let us have a look at. A 4-stage pipeline, meaning number of segments K is equal to 4. Okay. Now the thing is, what is TP? TP is maximum segment delay plus max register delay. Max segment delay is equal to 160. You remember TP? TP is equal to max segment delay plus max register delay, which is equal to 165. Okay. Now looking at this, we just need to find out the pipeline time for 1000 data items. Now the thing is, pipeline time is equal to K plus n minus 1 into TP. What is K? K is equal to 4. What is n? N is the total number of processes, total number of tasks, which is equal to 1000 minus 1. What is TP? TP is equal to 165 nanoseconds, which is equal to 1999 plus 4 is equal to 1003 into 165 nanoseconds, which is equal to 165.5 microseconds. Okay, the pipeline time in microseconds is equal to 165.5 microseconds, with which we have come to an end of the session on pipelining. I hope you got it completely, but understand carefully, if we get a question from the pipeline, it will be very easier to solve, since the formulas are having only one straight approach. There are no tricks, there are no tricks absolutely involved, right? So you just need to understand that if we get a question from pipelining, our life will become very, very simple indeed. We will be able to crack that question very, very easily within our fingertips. Okay, so that's it from the session. I hope you like the session, and if you do not subscribe to this channel, haven't yet, please do subscribe to this channel and like this session and share this session as much as possible. With this, Anil Sorumpudi is signing off, and any follow-up questions you can ask me right now. I guess we are completely done, with which any more doubts you can ask me. Otherwise, Anil Sorumpudi signing off. Thank you so much. Yeah. Thank you, Sri Lakshmi. Thank you, Krishna. And thank you, Anu. Thank you, whoever you are. Fine. Thank you so much. That's it from my side. Let me sign off.